Hello and welcome. I'm Mike, K6RRE. This is a discussion of a basic one-tube ham radio CW transmitter using a pentode or beam power tube. These transmitters were very popular between the 1930s and the 1970s. Here I'm using the Antique Wireless Association 6AQ5 one-tube transmitter PCB as an example. In this circuit, the 6AQ5 can put out up to 10 watts on 80 and 40 meters, depending on your power supply, but 5 to 8 watts is more typical. The transmitter circuit is what's called an electron-coupled Colpitts oscillator. This type of transmitter was very common from the 1950s to the end of the tube era. Electron-coupled means that the screen grid tube functions as both an oscillator and a power amplifier, essentially an MOPA, Master Oscillator Power Amplifier, design in a single tube. To start with, on the schematic, here is the tube, a 6AQ5. You can see the cathode, the control grid, the screen grid, the suppressor grid, which in this case is actually a set of beam-forming plates, and lastly, the plate. This is the oscillator portion of the transmitter. It's a standard triode oscillator with the screen grid acting as the plate of the triode. Starting at the left, we have the crystal. On this PCB, there is an option for either an HC49 crystal or an old-style FT243 crystal. Then comes the grid resistor. The grid resistor sets the grid bias and the tube operating point and is a critical component. If the resistance value is too high, you can get chirp on your signal, the power output goes down, and you will have a higher level of harmonics on the output. If too low, the tube simply won't oscillate. There is an option here for either a fixed resistor or a potentiometer. The pot lets you determine the optimum value of the grid resistor, and it's a very handy adjustment to have. Next are the feedback capacitors of the Colpitts circuit. C1 is optional. For most tubes, it's not needed on 40 meters, and it's a good idea to just leave it off to get a better note. For 80 meters, it will probably need to be included. In that case, a 5 or 10 picofarad capacitor is a good value to install here. The capacitors can be either mica or ceramic. Here is the RF choke that raises the cathode above RF ground. Any value between 100 microhenry and 2.5 millihenry will work. It does not have a large RF voltage across it, so it can be a physically small choke. The key connects to these pads, and if you want to measure cathode current, you can measure current between these pads. Otherwise, be sure and install a jumper wire between the current measuring pads. Finally, there is a key click filter that reduces clicks on key up. The plate circuit is where the oscillator output is amplified. The RF current from the oscillator flows through the screen and is boosted in power by the large plate voltage. At the same time, the screen grid isolates the oscillator section from the output section and the antenna, which results in minimal stress on the crystal and makes the design fairly insensitive to load and antenna changes. For the plate choke, you can install either a physically large traditional pi wound choke like a 1 millihenry or 2.5 millihenry, or you can use two physically small modern chokes in the 100 microhenry to 1 millihenry range. This transmitter build uses 100 microhenry chokes in both the cathode and the plate circuit. The plate choke does have a high RF voltage across it. When the smaller chokes are used in the plate circuit, there are two in series to split the plate RF voltage across them because a single small choke may not be able to hold up to the full RF voltage on the plate. The output capacitor couples the plate signal to the RF output network, which you will provide off-board. Make sure this is a good quality capacitor rated for at least 1000 volts. I've had a couple of cases where cheap Chinese capacitors used here have caused chirp in the output signal, and replacing them with better caps made the chirp disappear. Cheap caps don't seem to cause any problem in the RF bypass roll, however. The output network can be either a pi network or a link-coupled output. The pi network is more flexible and easier to adjust, but you have to come up with a suitable variable loading capacitor of perhaps 800 to 1000 picofarads for 40 meters and double that for 80 meters. For a link-coupled output, you will provide a tank tuning capacitor and a fixed inductor, and a link coupling to the inductor. You may also need another variable capacitor in series with the link to tune for maximum output. It will take some fiddling with the link to get optimum performance. The details of output networks are beyond the scope of this video, but if you choose to use a pi network, you can use the AWA pi network calculator to get the approximate values you'll need. In the screen circuit, there is a dropping resistor and 2 Zener diodes. Often you'll only need 1 Zener, but we've designed space for 2 just for added flexibility. If you only use 1 diode, install it at D1 and install a jumper wire at D2. The screen voltage you choose will be the main way you set the transmitter power output, along with the B+ voltage value that your power supply provides. Higher screen voltage gives higher power output up to a point. There are also 3 RF bypass capacitors in the design, here, here, and here. Down here is an optional resistor in the heater circuit. If your heater voltage is higher than your tube requires, you can drop the voltage with a suitable resistor here. Otherwise, be sure and install a jumper wire in this location. Here is a prototype transmitter on the bench to show it in operation. It's connected to a pi network output running through a wattmeter into a dummy load. The power supply produces roughly 300 volts DC, key down. If you're interested in building your own 6AQ5 transmitter, please have a look at the Antique Wireless Association website. There is a link in the description. They have a PCB for the 6AQ5 and also one for the 6V6, which can be used with a great number of other tube types as well, including the 6L6. They also have a PCB for building a high voltage power supply for use with tube equipment. Any PCB sales by the AWA go towards their educational mission and museum, so help them out if you can.